I'm sure you know how to find the volume of the solid generated by the area between A and B. Now, what I want you to tell me is how to find the volume of the solid generated by the area between these two curves. So in fact, you know what? Let me remove A and B, and I'm saying that there's an area between these two curves right here, and this area is being rotated about the x-axis, and I need to find the volume of the solid generated by that area. Now take note of this. Let me clear this out. What you must note is that the area under this curve, under the orange curve, extends all the way down here, down to the x-axis, and that's a very large area. Now the area between the green curve and the x-axis is merely here. What are the implications of this difference in area? What happens, is that when we take this area right here and we rotate it about the x-axis, we're going to get not merely a circle, but a hollow circle. Why exactly do we have this hollowed region in the middle? In fact, let me highlight it. It's hollowed by coloring the outside. Why do we have this hollowed region here? Because this part, this area under the curve, is left out of the rotation because we're only rotating here. We are rotating only the area between the green curve and the orange curve. What is that telling us? In finding the volume of the solid generated by rotating the area between two curves, we need to know which curve is the upper curve, which curve is the lower curve, and what we'll have to do is to subtract the volume of the solid generated by rotating the upper curve about the x-axis between the points of intersection. So we're going to find the volume of the solid generated by rotating the upper curve about the x-axis between the points of intersection, and subtract from that the volume of the solid generated by rotating the lower curve about the x-axis between the points of intersection. So if our upper curve is f of x and our lower curve is g of x, what is that telling us? That the volume of the solid generated by rotating the area between these two curves will be the integral of pi f of x squared with respect to x from a to b, if a and b are the points of intersection. And from that, we're going to be subtracting what? The volume of the solid generated by the lower curve between that same a and b. So that would be g of x squared with respect to x. And that would merely be it. So let's look at an actual example. So we have two curves. Our curves are y equals 3x and y equals x squared plus 2. So now we want to we need first of all to find the points of intersection. So from CSEC days, all we do is x squared plus 2 is equal to 3x. We need that all we have is an actual quadratic. So our roots would be x equal 2 and x equal 1. Since we have now found the points of intersection, we need to find out which curve is the upper curve and which curve is the lower curve. How do you do that? Well, we need to pick a point between 1 and 2. We're going to pick 1.5. If I substitute 1.5 in this equation, I get that y would be equal to 4.5. If I substitute 1.5 in this, I get that y would be equal to 4.25. So apparently, y equals 3x is the upper curve. So let's make some space. So let's do some integration now. It would be the integral of pi times, what's 3x all squared? That would be 9x squared. And we're integrating from where to where? From 1 to 2 with respect to x. And you're subtracting from that the integral from 1 to 2 of what? This function squared. That squared would be x to the 4 plus 4x squared plus 4. And we're integrating with respect to x. So this gives us pi times 3x cubed from where? 1 to 2. And we be subtracting from that now pi times x to the 5th over 5 plus 4x cubed over 3 plus 4x from where? 1 to 2. So you can substitute those for yourself, but we will end up getting 21 pi minus 293 over 15 pi, giving us what? 22 over 15 pi units cubed. So what we're being told here is that the volume of the solid generated by the area between the two curves y equal 3x and y equal x squared plus 2 would be 22 over 15 pi units cubed.